Yeah. Hello all. So basically, we've heard a lot about LLMs this evening, and I'm a bit here to remind you that sometimes old-fashioned data science is a really good solution, even when necessarily what you would assume is the perfect solution, which LLMs would be good for, is not always the best. So this is specifically about multi-tool deduplication. So first, about who I am. I started in the cybersecurity industry approximately a decade ago, and I fell in love with data and working small teams and startups. So data engineering or data science or even data analytics, I've probably done some of it. And currently, I'm the founding data engineer at Smithy Security. So this is some research I've been looking into for the past amount of time, and I'm hoping that you can get some insights from it. So the problem itself, as mentioned, is we like using lots of scanners to get large code coverage and be able to detect vulnerabilities of all different types. So Smithy Security specifically is a workflow engine where it can scan an asset, in this case, an arbitrary Git repository, with any number of tools, GoSec, SemGrep, or Nancy in this example, and then we want to output it in one place. So in this case, we can generate linear tickets to allow you to more easily solve and fix these vulnerabilities. Every single one of these tools independently raises a finding even on the same vulnerable section of code. So here, GoSec and SemGrep actually have significant overlap in their rules. And so this would generate two separate tickets and just lots of noise. And we would like to combine these findings automatically, so we're not raising any duplicate tickets or notifications, and it's a lot easier to deal with. So what are some potential ways to identify duplicates? Number one is location. If there is a vulnerability in the same place, it is likely to be correlated. However, multiple vulnerabilities can exist on the same line of code. It doesn't necessarily have to be the same thing. Also, tools are generally not great at reporting the specific location. Two tools can report the same vulnerability and give completely different line numbers. CVEs would be the gold standard as a way of matching. Most tools don't report CVEs. CWEs are similar. They would be very useful for relevance, but they're often too vague for matching. And also, most tools, again, don't report CWEs either. This leads to descriptions, which is natural language processing. This is commonly what LLMs would be used for and seem like a really ideal use case for it. But it can be hard to give confident results. And then finally, another possibility is human in the loop. We could use people to check whether this is correct or not, but this is a really slow manual process, and we want an automated solution. So let's look at some examples. Here we have a GoSec finding of string concatenation. It's a very simple one. At the top here, we have the title, and we have the description, which in this case is basically identical to the title. And we have a bunch of metadata, and note there is no CVE or CWE associated with it. And the exact same finding from SemGrep is completely different title, completely different description, but this is the same finding manually checked. And also, if we compare the metadata itself, they can't even decide that they're the same severity or the same confidence, and they're just no related fields whatsoever. So this leads us with one option, which is the natural language processing, or NLP. So as kick us off, a quick example would be to use Python and spaCy to compare the similarities between it. And this is where it gets kind of mathsy. So here we can translate individual words into their semantic meaning, which is a specific numerical vector about its encoding and its meaning. And then we can get the average of all of these meanings in a sentence to get the vector meaning of the sentence and compare the two together to work out how similar they are. So as a very quick example, we have our long description here and our short description. And this gives a similarity between 0 and 1, in this case 0.5, which is quite similar. So that's pretty good. But it's actually not. It's terrible. And it's terrible because when we compare it to a completely different example, use of weak random number generator, instead of SQL, it's a lot more similar. It's 0.8. So it's completely in the wrong direction. And this is because wordiness generally, and also the fact they're both marked as cybersecurity sentences, has a lot stronger correlation than the actual meaning of the sentences themselves in this example. So there are some approaches we can use to make this better if we're looking at pre-processing. So here we can tidy up the text so this language model is easier for it to parse. So a bunch of stuff, but we can extract the noun phrases and make it like more basic sections of it. Lematize, so this is turning them into like their stem words, so queries turn into query, as an example. Remove stop words and the but, so we only keep the useful stuff. And also remove duplicate words, so we're not oversaturating it with the same word. And here we can see, once again, we got the long one, SQL injection, compared to the short one, SQL string concatenation. That hasn't changed very much. And this gives a much higher similarity now, 0.7. But if we do the same to the other random one, the similarity is now also 0.7. So they think they're the same. So that is still, sadly, entirely useless in this case. Moving onwards, we can now use a more traditional LLM. So in this case, a sentence transformer. And these are LLMs specifically optimized to look at the meanings of sentences and encode it into a vector again. And this does it the entire text rather than individual words. So here, the fact that it's cybersecurity should be a lot less significant, and it should more understand actually what's going on. And we got a long example again. And here, compared to the short one, 0.4. It's not great. It's not particularly confident. But the use of the weak random number generator, the unrelated one, is minus 0.5. So this is a lot better, and it's a lot more in the right direction. But this has a really big downside of that. It's not confident. It's also very painfully slow. LLMs always are slow, as I'm sure many of you have come across, let alone when you run and host your own model on your own laptop. For 8 examples, took me a minute to run on my laptop. Of course, productionized, it would be faster, but this is a really bad starting case. And because of this, LLMs really aren't suitable for this use case generally at all. Firstly, experimenting with different models, either professional models using APIs or other specialized models, generally give much worse results as well. This was one of my better examples. Models are hugely expensive and slow. And finally, we have to scale up to 100 million findings per day in this scenario. We cannot spend a minute processing 8 findings. So we really have far, far too slow and very, very expensive. Even if we want to ship it out to a server farm, that will cost huge, huge amounts of tokens. So we got to find a much better way. So let's go back to data science instead of this large language model world we've been living in. So previously, as I showed you, we had attempts at pre-processing, and we had these results. We had SQL injection, string, blah, 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 SQL string concatenation, and SQL injection, string, and crypto random. So to a human, someone who doesn't even know anything about cybersecurity or these vulnerabilities, these are obviously a lot more related than these are. But the model can't see it at all for some reason. So there are a lot simpler approaches. One example is bag of words. So here we can literally count the number of times we see each individual word. We can go SQL injection, we can see SQL a few times, and this has it. And this doesn't have SQL at all. So the more similarity between the words, the more they match. And then we can weight it as well by how important the word is across the corpus. If every single description says vulnerability, that's probably not an important word. If only a couple of the descriptions say SQL, that probably is a very important word. So with a little bit of maths, we can work out how. I think that's frozen. Oh, there we go. I just had to press harder. So with a little bit of maths, we can work out far more how similar they are by counting the words, dividing it by how important the words are, and they get a new similarity score. So with this in mind, we can build a new corpus. Here are 6 examples, which are actual descriptions from different vulnerability tools. And then we can give it an unseen example before. So this is one not in the corpus, brand new. And we can find the best match. So a use of weak random number generator is the best match of do not use math.random. This is a correct match in this case between a semgrep and a GoSec finding. And it has a quite high similarity, 0.7, which is above our threshold. So we can say that works. Moving onwards, this is the one that was previously giving us such bad issues, SQL string concatenation. And it has, once again, found the best match with a similarity score of 0.5. So this is more confident than the LLM or any semantic matching gave us. And it's once again above our threshold, so a confident match has been found. And then finally, another random example to show it's not constantly giving false positives. It has found a best match, but its similarity is 0.1. So the similarity is between 0 and 1. 0.1 is very not confident. It doesn't think it's related. That's lower than our threshold. And so we can say, hey, this is unrelated, and discard it. Lots of advantages on this approach over use of LLMs. So consistently gives the best match between, as we saw previously, sometimes it didn't. Doesn't flag on false positives. It's really, really fast. So it sounds quite simple. At the end of the day, it's basic maths, which is what computers are really good at, and so scales really well. It can be trained and applied in separate steps. So we can build a model on one set of data, not have to touch the model again, and then just apply it really fast on other client systems. And it's for me, this is very important. It's incredibly explainable. It's not a black box like other LLM solutions. I can look in it. If something's not working right, I can tell you why it's not working right. If something is working right, I can tell you how and tweak the weighting specifically myself very easily, which gives us the final deduplicated issue. So as you saw previously, there were two separate things. Now we can get an automatically detected best title. This one's from GoSec. And the best description, this one's from SemGrep. And we can show it and raise it in one ticket, significantly reducing noise for clients and people who want to do this. We have found when talking to clients that they really want to add more tools, and this can be expanded with as many tools, as much overlapping coverage as you need, and keep on keeping that noise quite low. So that is a whistle-stop tour of it at 10 minutes. So thank you. There's a lot more I could go into around other use cases of when LLMs are not best compared to data science, or how to productionize this. I just talked about the science behind it instead of actually how it works. But if you have any questions about any of that, please don't hesitate to ask.
Wonderful.
Thank you very much.
Oh, I can say questions straight away. Go for it.
Yeah, you mentioned that sometimes you also get different severities, right? How do you pick the right one then?
Sorry, sometimes you get difference of what, sorry?
Different severities and different other keywords.
Yeah,
right?
so it is an issue. Tools regularly report the different one. Most of the time, we just go with what the highest tool reports. Generally, if one person thinks it's really high severity, users probably want to know that instead of us suppressing its severity. We have the option as well of our own enrichments, where we can look into like if things are exploitable or not. So if you saw in the example, we had like SMIVI priority as well as the severity. SMIVI priority is how important we think it is, which is a little bit more intelligent, but we always report the tool severity and the highest tool severity there.
Yeah. I have a question, right? Yeah. So basically, when you were doing the LLM exploration, right? In terms of actually trying, did you try to speed it up by using a laptop with NVIDIA card and things like that? Because when you said, regular laptops are slow, but was that the kind of, did you try to throw in more hardware there at the beginning?
So my ones, in my specific, when I self-hosted the LLMs, I didn't try and throw in more hardware. I did use APIs at some point, like to connect to like Gemini. I used Gemini keys and stuff. And even then, with all of their server farms of Gemini Pro, the results were still took seconds to respond for one result. And like I said, when we're scaling up to like 100 million findings a day, like even 4 or 5 seconds a result is really quite slow, let alone the cost associated with it.
How do you know that the findings, the line numbers are not the same, are actually the same?
So, so quite a lot of this was, I will say, me looking at some manual outputs of tools, swearing a bit before I worked out where I needed to go. So the examples for this presentation where I was manually verifying that these were the correct things. Normally, the finding line numbers are close. So the first pre-processing step, so I'm not comparing all of the 100 million findings against each other, is to do an approximate location check. So one could report on line number 70, and one would report on line number 68 to 72. And as they're within a threshold, I can then compare these two automatically instead of just going to everything.
Last one. So you have the magic really happens with the bag of words.
Bag of words, TF, IDF.
How do you?
How does bag of words specifically work? It is, so bag of words is something that is used by lots of companies. I think Gmail originally used it. But what it does is, at its most basic state, it literally counts the instance of every single interesting word. So I've already lemmatized and stripped out all the stop words. So in this case, it counts how many times SQL is seen. And then when you can get a bit more complicated for the layer above it. And then what that does is it works out the importance of every word. So it counts how many times SQL is seen across the entire corpus. So every single description we have. And then we can get a relative importance rating for each word and times it by how many times we see that word. And then from there, we can get like weight matchings between descriptions.
Okay, thanks so much, Peran.
Thank you very much.